14.2, today we're going to take a look at multistage experiments. And if you ask somebody who's taken this class before, they're probably going to groan if you talk about what this section is. You're going to draw some pictures, and you might run out of space when you draw the pictures, and it's going to be okay. But we're going to work with what are called tree diagrams. Okay, that's what's going on in this section is tree diagrams. And it's not like factor trees, although it kind of looks a little bit like them, but it's going to be doing something a little bit different too. All right, so leading idea. Multi-stage experiments in probability involve a sequence of events, each with its own uncertainty, where the overall outcome depends on how these stages combine. Similarly, faith in God often involves navigating a series of life experiences, each with its own challenges and unknowns. Just as probability helps us reason through complex, uncertain sequences step by step, God invites us to trust through each phase of life, believing that even amid uncertainty, there's purpose and He will guide us in the journey. So before I pray, let me just kind of make a comment to this, because this happened in my house recently. We were talking about the fact that, so we've lived back in Oklahoma now for about 16 years. And our move back to Oklahoma is home. Like it was valuable to move back just for it to be home. But when we look backwards at the series of events that led to that and where our family is today, I can pinpoint some very specific things that would be very different in my life if we had not moved back to Oklahoma. Number one, at that time, but also just at all, because we were looking at just getting back closer. So we could have ended up in Texas or Arkansas, and that would have been closer, and we would have been okay with that as a result. So most of my children that are in my family, with the exception of Abby and Eli, wouldn't be in my family at all. So Jewel and Cam wouldn't be, because they were adopted through the state of Oklahoma. If we weren't in Oklahoma, that would have never happened. And then my 3 Ethiopian children that are here would never have gotten here. And the reason I know that is because the only reason I ended up in Ethiopia and met those children was because I went on go trips through OBU. So this certain events kinds of things is very cool when you look backwards at how that all played out. So let's pray. Dear Heavenly Father, I thank you so much for your hand at work in our lives. I thank you that in the middle of uncertainty that we can trust that you have a plan and that your plan is for good. I thank you for this day. I thank you for this opportunity to take a look at multi-stage experiments or at the series of events that can happen from a numerical point of view, but we also recognize that we trust you for final outcomes, and we thank you for that. In Jesus' name, amen. So vocabulary is going to show up first, of course. A tree diagram. I already mentioned it by name, but what a tree diagram is a sample space model where each outcome is designated by a separate branch. We talked about the word experiments last time. It doesn't mean science, right? It's any activity. So a one-stage experiment is an experiment that is over after one step, one set of branches, right? So this is the family that says one and done, right? One child, it's done, not having any more. Experiment over. Multi-stage experiments, or in this case, we're talking 2-stage experiments, are experiments that are over after 2 sets of branches. Okay, this would be the equivalent of my scenario to saying you have 2 children. Okay, or you roll the die 2 times, or you draw 2 cards. Make sense? Okay. Oh, too fast? Are we good? We're good? Okay. Theorem 9.6 talks about how we use our tree diagrams in order to find these probabilities that we're going to be working with. It's the multiplication rule, and it says for all multi-stage experiments, the probability of an outcome along any path of a tree diagram is equal to the product. What's the word product mean? Multiplication, right? Of all probabilities along the path. So we're going to multiply a bunch of numbers together. And this note, highlight it, circle it, bold it. I don't know what you want to do, but it's really important. There's going to be places along the way where you're going to say to yourself, I don't need to draw a tree diagram for this. I understand what numbers I'm going to multiply and what it's going to look like, and I can just skip that step. And I'm going to tell you, please don't. because while you can reason through that as a 18, 19, 20, 21-year-old, the children that you're working with, 11, 12, 13, they can't do that, okay? So this is kind of like what was happening when we were doing algebra tiles and when we were doing hands-on equations. We're working under the premise of what would my kids need to do in order to be able to access this information. Now, tree diagrams is not the only way to draw some of these, so I'll show you some other models, but there's going to be ways that you're going to mimic these or show these, and they need to be shown each time. Good? Okay. Independent events. Now, I mentioned this word last time, though I never defined it. Now we're going to. Independent events are events in which the occurrence of one event has no influence on the outcome of a second event. This showed up specifically in our example toward the end, where we were looking at a student or a person who had flipped. It was flipped a coin 5 times. Do you remember that? And it came up, let's say heads 5 times. I don't know if that's true or not, but that'll work. Came up heads 5 times in a row, and we said, or the student or the person thought it's going to come up tails more likely the next time. And we said that doesn't work that way because every flip is a standalone experiment. There's no outcome from the first experiment that affects anything for the second one, right? They're independent of one another. They don't affect one another. And when you have independent events, what happens is that the probability that 2 events happen then, when they have no way of affecting each other, is simply the multiplication of their individual probabilities. So probability of event 1. So probability of flipping that coin the first time times the probability of flipping the coin a second time, and it landing in a certain way. So we get these to be multiplied. Now, if you have events that actually interplay and affect each other, you have to be a little bit more careful. Things don't work out quite as friendly. But we can kind of get around that if we're careful about how we draw our trees. And that will be good news. I think we're ready for an example. Is that true? Okay, I think our people are going to Hawaii. Are they? Oh, they are. I remembered right. They're going to go to Hawaii. An executive committee consists of 10 members, 4 women, 6 men. And 3 members are selected at random to go to a meeting in Hawaii. You signing up? Sounds good to me. Okay. So what's happening here is that we have 10 different people, but the way in which we're categorizing them here is by male versus female. So while, yes, there are 10 different people that can be selected, the part that's restrictive here is what gender they are. Y'all with me? So when I draw my tree diagram, I don't need 10 different outcomes. Yes, there's 10 different people that can be picked, but when we're only considering whether they're male or female, there's only 2 different outcomes that can really happen. So a tree diagram starts out looking like this. The first one is going to be male, female, like that. Draw it with space, spread it out, okay? Top of your paper, bottom of your paper for the space that you have. Write small, write neat. We're gonna fill this up with space. It's gonna be completely full when we're done, okay? How likely are we going to be to select a male? So imagine that all their names are put in a hat and we're pulling out a name. How likely are we going to be to select a male as our first person to get to go to Hawaii? Is it 50-50? Ooh, it's not on this one. So if it were just male versus female of maybe a general population, 50-50 would seem reasonable. Why is this one not 50-50? Because there's not 5 of each. This piece right here is where we're going to pull our stuff from. 10 members, but 4 are women and 6 are men. So what's the likelihood of selecting a man? 60% or 6 out of 10. I'm going to do these with fractions on this one because in my next step, the decimals would be awfully ugly. So we're just going to go with fractions for this. So if I have 6 out of 10 chance of selecting a male, what's my chance of selecting a female? 4 out of 10. Fantastic. Everybody good? Okay. Now we have selected that one person and they're already, getting the ticket ready for them to go. And we still have to select a couple more people, true? So this is another event, right? It's a separate event from the first one, but the first event does have bearing on the next outcome. I'm still going to either get a male or a female. That part's the same. But I no longer have 10 people's names in the hat because one of them's already been drawn out and it doesn't go back in because he can only go to Hawaii on the trip as him one person, right? I mean, he's not going to take 2 seats on the airplane. I mean, I hope he doesn't. That would be kind of sad. Okay, so nonetheless, how many males are now currently in the hat? 5. How many names are currently in the hat? 9. So these events are not independent in the sense that they don't affect each other, right? It will depend on whether or not we selected a male to start with. Because if I'm going to come back to the female just a second. If I come down here to the second set of branches, this is sort of the outcome that would have happened if the female's name had been drawn, right? I drew a female's name. So if I drew out a female's name, how many men are still in the basket? And that's 6 out of 9. So the 5 out of 9 at the top, the 6 out of 9 at the top, they're different. And they're different because these aren't independent events. But I'm separating the probabilities out so that I can still work with them in a way that's helpful and allows me to use that probability formula on the previous slide. Okay, let's do the females. If I selected a man the first time, what's the likelihood that a female's name will get drawn on the second draw? 4 out of 9. If I selected a female the first time, what's the likelihood that the female's name is going to get drawn the second time? 3 out of 9. Now, I don't know what's happened because this is sort of showing you all the cases, right? But I do still need to select a third person, right? So this is choosing person number 1, first set of branches. Second set of branches, choosing person number 2. I need a third set of branches. The third set of branches are 2 more branches coming. You see what I'm telling you about drawing these? Who's run out of space? You guys are doing good. Nobody's run out of space yet. Fantastic. And they all have the same description, male, female, male, female. Feel free to abbreviate MF if you wish, or man, woman, or something like that. Now, a completed a completed tree diagram includes having probabilities along all the branches. So we've got to fill in now 8 probabilities here, right? But every probability that I look at is going to be determined by what happened previously on the diagram. So I'm going to do the top branch first. On the top branch, I selected male and male. How many, if that's what's happened thus far, how many males' names are still left in the bucket? 4 out of 8 this time. Very good. How many female names? 4 out of 8. If I'm along the second set of branches, right, male, female, right, here, if I'm there, I've got 1 man that's already been selected, 1 woman. How many men's names are still in the basket? 5 out of 8. How many female? 3 out of 8. Okay, moving right along. This one right here is the same scenario as the last one. It's female, male. The other one was male, female. The order in which they were picked is different, but the outcome is the same and the probabilities are actually going to be the same as well. So when I'm looking at this one, I actually have 1 man and 1 woman already selected, which means how many men are still in the bucket? 5. And how many women? 3. So this set of numbers matches the one above because those outcomes are actually the same outcome. Last one, I've selected 2 females. How many males' names are still in the basket? 6 out of 8. And then how many female? 2 out of 8. Okay, everybody good? This is a completed tree diagram. Okay, how are we feeling? Feeling okay so far? Okay. The majority of the work is tied up in creating the diagram. Okay, this happens in number theory when we create Venn diagrams, for those of you who've had that class. The majority of the work is tied up in creating the diagram. Then we end up with a series of questions that the diagram will help us to answer. The first one says, what is the probability that all 3 selected are women? So if I look back at my diagram, that is asking me for this specific outcome, correct? And over here, The multiplication rule for tree diagrams says that the way I find out how that outcome actually plays out is by multiplying the individual probabilities along that branch. Okay? So we're going to multiply the probabilities along this last branch. The 4 out of 10, the 3 out of 9, and the 2 out of 8. So over here, we have 4 out of 10 times 3 out of 9 times 2 out of 8. Can you express it in decimals? Can you express it in fractions? Yes and yes. You can do either one, and it would be perfectly acceptable. I'm going to do this one with fractions. We'll do other ones with decimals, but either are fine. This one has some nice things that simplify, right? 3 and 9 actually both reduce. They divide by 3. 2 and 8 both reduce. They divide by 2. 4, actually here we'll cancel flat out with that 4, right? Diagonals. And I don't think I have much left. There's a 1 on top now, and there's 30 on bottom. Does that look right? 1 out of 30. So there's a 1 out of 30 chance, not very high, that all 3 of the people who get to go to Hawaii are women. Does that make sense? Okay. Part B actually pushes back into something we did last time. Part B says, what is the probability that at least one man is selected? Okay, so if I want at least one man selected, what I don't want is all women. You guys with me? So I'm going to write that down. This is the opposite of all women. And we had a notation for that last time. We called it the complement. And it looked like A with a bar on the top. Now, if you recognize that, we had a formula that said the probability of finding an event is 1 minus the probability of the complement. And we already found the value, probability-wise, for getting all women. It was 1 out of 30. So if we're thinking about it from this perspective, I have 1 minus 1 over 30, or 30 over 30 minus 1 over 30, and I get 29 over 30. If you're not thinking about it that way, let me show you what you end up having to do. And then you're all going to be like, never mind, that was great. Let's go back. So if you're not thinking about it as a complement here, you're looking back at your tree diagram and you're going to select every branch that has at least one man along it. That's this branch, and 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 it's this one, and it's this one, and the only one it's not is the one at the bottom. Are you with me? If you don't use the complements principle of counting, what this means you have to do is multiply along every branch. That's 7 set of multiplications. And then you have to add those values all up. That's a lot of work. Y'all with me? We don't want to do that. We don't want to multiply 7 things out. We multiply something out 7 times and then add them together. Especially when all I really have to do is just 1 minus the one thing I don't want to have happen. Okay? The complements principle of counting is involved. So then, let's take a look at another one where I'm going to show you an alternative to a tree diagram because it works nicely. A tree diagram will work with this one as well, but I want to give you some options when they present themselves. And this is one that does. A box contains 5 slips of paper, numbered 4, 6, 7, 8, 9. A player reaches into the box and draws out 2 slips and adds them up. If the sum is even, the player wins. If the sum is odd, the player loses. Okay, can you picture the event happening? Can you picture the scenario, the experiment, and how it's working? So we could do a tree diagram here. If we did a tree diagram, we'd write out 4, 6, 7, 8, and 9 in the same places that I wrote male and female. Okay? And then off of each of the 4, 6, 7, 8, and 9, I'd write all the other numbers listed. And the tree diagram looks really messy. Agreed? Can you picture what that would look like? It'd be a really big tree diagram. So let me show you another way that we could do this instead. We have two numbers we're picking. So I could pick the numbers 4 and 6, 4 and 7, 4 and 8, 4 and 9. That's 4 different ways I could pick two numbers, true? And in fact, it's the only 4 ways that I can pick the number 4 and include it with something else. So I could also select the number 6. I don't need to list 4 and 6. I've already shown a 4, 6 value. So I could have a 6, 7, a 6, 8, or a 6, 9. And those 3 6 values with the 4, 6 from the previous column, that would be all my 6s, right? Okay. But I could also have a 7, 8 option and a 7, 9 option. And there's one more. What am I missing? 8, 9. These are all the ways that I could draw 2 slips of paper. So this would be a sample space. We talked about sample spaces last time. So if I was like drawing out, curly braces and I was listing them sort of maybe like as ordered pairs or something like that of my draws, this would work. And this is a very nice sample space. What's the probability the player wins? Well, how did the player win? What did it say they have to do with those slips of paper? Add them together. And the goal is to add them together and decide if they're even or if they're odd, right? Okay, so let's add them together. I'm not going to write down the sum. We're just going to star the ones that are even or odd. Okay, we'll do the even ones. So if I add 4 and 6, is it even? Yes. Sorry. If I add 4 and 7, is it even? No. If I add 4 and 8, is it even? Yes. If I add 4 and 9, is it even? No. 6 and 7? No. 6 and 8? Yes. 6 and 9? No. 7 and 8? No. 7 and 9? That one's actually a yes. And 8 and 9? No. So I've gone back and I've chosen by starring them, all the options that let me win or let the player win. How many of them are there? 4. But how many total options are there that were listed? How many were there? 10. I was like, I think there's 10. You're welcome to put that in decimal form if you want. That'd be 0.4. You're welcome to put that in fraction form if you want by simplifying and dividing by 2 on each of them, and that would be 2 out of 5. I'm going to put it in fraction form still, 2 out of 5. Now the thing says, well, let's change the rules and let's say that the numbers are multiplied instead of added. Are you with me? So all my blue stars are going to go away and we're going to star in red all the ones that are going to be even when I multiply them. 4 times 6, yes or no? Yes. 4 times 7? Yes. 4 times 8? Yes. 4 times 9? Yes. Now I hope you realize nobody's really multiplying 4 and 7, 4 and 8, and 4 and 9. I hope they're not. Because the truth is the fact that you're multiplying by 4 automatically makes it even. True? That also makes all the 6s even, right? Because 6 is even, and if I multiply, I'm going to get an even number. And all the 8s are even. There's only one that's up there that's odd and odd, which gives me an odd number. So if I win by getting an even from multiplying, how many ways can that happen? 9 out of 10. That's in reduced form. So does it change? Yeah, it changes. If so, what does it change? It should say, what does it change to, I think. To what does it change? I read it wrong. So if so, to what does it change? And the answer is 9 out of 10. Okay? All right, let me show you one. Actually, I think let's pause there. This is a good place to stop. We'll pick up with example 3 next time.